Okay, welcome. This is second to last lecture. We have almost finished with the semester. Just have a couple more things to cover, mainly interfacial cycloadditions and sigmatropic rearrangements. Now, I don't have to tell you, it's been probably the most unusual semester I've ever had. And so, therefore, I'm going to do something that I've been asked to do before, constantly around this time of year, during all of my lectures, and I just have refused. But this time around, I'm just going to go ahead. Sure, you guys really deserve this. So today, we are going to hold this lecture outside because it's a beautiful day. Birds are singing. Skies, nice blue skies. The groundhog isn't out yet, but I'm sure he'll be out there mowing the lawn any moment now. So enjoy, since we're going to do this lecture outside. Okay, so the cycloadditions we've covered so far have been superfacial, meaning occurring on the same face. There are also some anterofacial cycloadditions that are possible, which means occurring on opposite faces. Now, I've got a demonstration that's pre-recorded that I'll insert into this video, explain the difference in just a bit. But these terms are related to the Woodward-Hoffmann rules. Where conrotatory and disrotatory, written in blue, refer to electrocyclic reactions. So those are the ring opening and ring closing. While superfacial and anterofacial refer to cycloadditions and electrocyclic reactions. So, if you have two alkenes and react them together, in order to do a superfacial reaction, you need light. Because if you just simply heat them up, no reaction. Now, it's no reaction because the anterofacial has a tendency to be very hard to pull off. It's very sterically crowded. But there are certain anterofacial reactions that can occur, and that's the reaction of a molecule called a ketene, which has a carbonyl directly attached to or part of an alkene. So it's a ketene and an alkene. Heat these together. You can do a 2+2 reaction to form that. Okay. Now we're going to cut into the pre-recorded video. Hello, and welcome to this rather put together demonstration about interfacial cycloadditions versus superfacial cycloadditions. So to kind of give you an example, the Diels-Alder reaction, of course, is between the HOMO of the diene and the HOMO of the diene looks something like this. Like so. Now, and this HOMO of the diene reacts with the LUMO of the dienophile, which is essentially an alkene. Like so. And if we're to shade it, we have the one node there and the one node there. Now, a superfacial interaction is the HOMO comes in and reacts, and you see that there's a good interaction between this shaded lobe and this shaded lobe, and this unshaded lobe and this unshaded lobe. So that's what's called a superfacial interaction, reacting with the same face of this. In this case, we're reacting with the bottom face, and then we're reacting with the top face of this one. Okay. Now, alkenes just don't react with each other superfacially, except under light conditions. Because this right here represents the HOMO of an alkene. And so if we had the LUMO of an alkene try to interact with it, we would have good overlap here, but bad overlap right here. And so as a result, no reaction occurs. Because you need a reaction between a filled orbital and an unfilled orbital. Okay. Now, what an interfacial reaction is. I've got this upside down. So this will be the top. This will be the bottom, is a reaction that reacts with both the top and the bottom of a molecule in an interfacial cycloaddition. So what that looks like is, here we have the HOMO that's filled with electrons, and it's going to react with the top and the bottom half of the LUMO. And what that looks like is simply like this. It comes in crosswise. So here we're reacting the bottom of the HOMO with the top and the bottom of the LUMO. Okay, so instead of doing a superficial interaction that's sliding like this, you're doing an interfacial one. Now, the problem with interfacial interactions is they are sterically pretty hard to do, because keep in mind, in the case of an alkene, we have substituents coming out. In this case, if you just use ethylene, those substituents are hydrogens. And hydrogens aren't that bulky, but they are bulky enough that when this comes in, it hits one of those hydrogens and bounces away, and so on and so forth. So as a result, interfacial reactions are sterically disfavored because of that. Hits the hydrogens, and bounces off. It just has a hard time doing this. Now, in the case of a ketene, we don't have these hydrogens here. Those hydrogens are gone. Instead, we have an oxygen over here that's in the plane. And as a result, when this comes in, it doesn't have that steric incumbents. It doesn't have the hydrogens here to block it. So this is sterically unencumbered enough to go, and then you have the good interactions right here, shaded with shaded, or you could have even had unshaded with unshaded. But either way, you have a reaction between a filled orbital, the HOMO, and an unfilled orbital, the LUMO. Okay, so that's the demonstration. Don't know if I'm in focus or not, but who cares? Just want to thank you all for your patience this semester. And a lot of things went wrong, a lot of things went right. And in these troubling times, I'm just really glad that we're all able to keep a sense of humor, hopefully a sense of humor and everything like that. And hopefully this demonstration wasn't too bad. My other option involved toothpicks, paper clips, painter's tape, Q-tips, cotton balls, and beet juice. Yeah, don't ask. It did not work out, and now I have a mess to clean up in the kitchen. So, anyways, hope everyone is doing well, and we will talk with you later. Welcome back. So that's how the stereochemistry works. The mechanism of the reaction is still a concerted mechanism where you form both bonds at once to give that. Now, where do ketenes come from? And the answer to that is acid chlorides. Turns out, if you treat an acid chloride with triethylamine, and if you let it sit without a nucleophile present, it will eventually do an E2 elimination, giving a ketene. Now, ketenes themselves are highly reactive and react right away. So typically, you'll generate your ketene and then add in your alkene immediately. This molecule, ketene itself, is actually so reactive, it reacts with itself, another molecule of itself. To form a molecule called diketene. And turns out this molecule is commercially available. And if you heat it up, this ketene reaction is actually reversible. And so if you heat the diketene up, it'll split into two, and it's going back and forth between the states, and while it's here, you can use the ketene. Now, this is a great way of using ketenes is a great way of making four-membered rings. And one particular four-membered ring that's really good at making is what's called a beta-lactam. You make those by reacting a ketene with an imine. Like so. We're not going to worry about the stereochemistry of this reaction, but typically when ketenes are involved, the major product is usually the least sterically favorable product due to the interfacial reaction. That's also one of the reasons why Vidic reagents, I should say non-stabilized Vidic reagents, give Z isomers. It's because it involves an interfacial reaction to give you the least favorable four-membered ring. But anyways, this is what's referred to as a beta-lactam. Lactam is a specialized word for cyclic amide. And it's called a beta-lactam because here's the alpha carbon of the carbonyl, here's the beta carbon, the amine is attached to the beta carbon. Now, you may have heard of the term beta-lactam before, and here are some pretty famous beta-lactams. This is penicillin G. This is amoxicillin. No, not amoxicillin. Excuse me. Methicillin. Both of them are used in antibiotics. In fact, a lot of antibiotics have this beta-lactam structure because what it does is it has a tendency to disrupt cell wall synthesis, and that's one thing that a lot of bacteria have that our cells do not, making it a prime target for molecules that kill bad bacteria but leave us alone. I shouldn't say bad bacteria, I should say a lot of bacteria with cell walls. Thing is, a lot of bacteria have been developing, not really developing actively, but some of them just by evolution now have enzymes called beta-lactamases that find beta-lactams and cleave them and break open that ring, rendering these impotent. And so as more and more beta-lactam as more and more bacteria are developing these beta-lactamases, that's making a lot of our more useful antibiotics, well, essentially out of date. And so new antibiotics need to be discovered that counteract this. By the way, methicillin, you might have heard of MRSA. It's basically the superbug, one of the bacteria that people are afraid of because there's very few antibiotics that can actually kill these things. And M of MRSA stands for methicillin. The rest is methicillin-resistant Staphylococcus aureus. So this is one of the bad superbugs. Okay. Let's see. Now, that's a use of ketenes. Now we're going to switch directions and cover the last of these reactions, and that's the sigmatropic reactions, or sigmatropic rearrangements. And we'll have a few of them to cover, and we're going to mainly focus on what are known as the 3-3 rearrangements. And then on Friday, we'll cover hydrogen and alkyl shifts, other types of sigmatropic rearrangements. Okay, so the 3-3 sigmatropic rearrangement. This is by far my favorite reaction. if you take this molecule right here and you heat it up, the molecule you get is this. I mean, you cannot get a cooler reaction than that. Oh yeah, by the way, this reaction, it's reversible. Isn't that awesome? Now, to really fully get how this reaction works, it's a good idea to use deuteriums. So when you heat this molecule up, and again, this reaction is reversible. Well, let me draw that a little bit better. I'm running out of space. Like so. I mean, isn't that awesome? I mean, it's just a really neat reaction. And the best part is, it is just one mechanistic step. It's a concerted reaction. And if you want to see the mechanism, I'm sure it's basically this. And for it to number it, get there. So this is what's referred to as a 3-3 sigmatropic rearrangement. Where it gets its numbers from is you start by finding the bond that's moving. That's this bond right here. That's a sigma bond that's moving, I should specify. And then you number on either side of it, you count until you get to the spot where the bond is formed. And that's right there. And for those of you that are trying to track it, another way of showing it, if I draw it like this, keeping all the atoms in the same orientation, you get that. And that is just awesome. Okay. All right. So, I'm going to pause real quick and bring it indoors because there seems to be a lawnmower out. And we will resume. Okay. Now, this requires heat to get the reaction to go. You can actually lower the amount of energy necessary for this reaction because if you make it that single bond want to break, that sigma bond breaking, and the way to do that is you put a strained ring there. You give it some reason to break. And that way, you end up alleviating this ring strain. And so now, as a result of this reaction, you have something like this. As opposed to the earlier reaction, that where the energy is the same on either side. Here, there's a definite triangle. Now, if you want to really mess with this molecule, what you can do is you can add a CH2 right here and attach it to both those alkenes. And then, when that sigma bond moves, you end up with this molecule, which is the same. So it's suddenly reversible again. Technically, the top one is reversible, but the amount of barrier energy necessary to go backwards is even higher than going forwards. So, not going to happen. Okay. Now, a chemist who had the nickname of Bull, his last name was During, so he had the nickname of Bull During, he looked at this molecule and thought, what would be a neat molecule to make would be if you take that basic molecule okay, so that's sort of drawn in kind of 3 dimensions right here, and you link the two CH2s by an alkene bridge, like so. Then what you would end up having is a 3-dimensional version of this right here. Where this bond can break and move, this bond can move, out of colors here, let's go green. No, I don't want to learn more. Or this one can move. Let's go back to red. So any of those 3 bonds can actually move because of the alkenes. And as a result, there are lots of different isomers of this. That bond moves all over the place, and at certain temperature, it's to the point where it's no longer between just any carbon, any 2 carbons, it's everywhere. It's rapidly going from one side to the other. For example, if moves that side, let's see if I can even draw that. Say the red side moves. Then you end up getting that, like that. Which should actually be the same as that if I draw that alkene right. There we go. That's just that rotated on the other side. But in essence, that bond is moving everywhere. And because it's moving everywhere, in this case, there is only one signal in the proton NMR. And that's kind of incredible. Now, if you cool it down, you get more and more signals, but at a sufficient temperature, there's only one signal. Now, these molecules, where that bond is moving back and forth, are what we refer to as fluxional molecules. They are not resonance structures. Resonance structures are molecules that basically represent the same molecule, just where their electron distributions in orbitals are different. Here, the bond, the connectivity, the sigma bonds have changed. If you take a fluxional molecule and cool it down to 0 Kelvin, you can stop that bond from moving and you get distinct structures. In case of resonance, if you take it down to 0, you don't get distinct structures in resonance. It's a big difference between resonance and other structures. Resonance represents the same molecule. Okay. So, these are examples of what are called a Cope rearrangement. And the way to look out for Cope rearrangement is to look out for this pattern of double, single, 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 double. And you'll particularly see this when here, on this bond right here, the middle single bond has a strained ring for a driving force. Very similar to the Cope is what's called the Claisen rearrangement. In the Claisen rearrangement, it looks an awful lot like a Cope, except you have an oxygen in there. The thing about the Claisen rearrangement is its driving force is a carbonyl. It is still a 3-3 sigmatropic rearrangement, but having the double bond O introduces a significant amount of stability, giving it the driving force to have this reaction occur. Now, a more popular use of the Claisen condensation is to add carbons ortho to an OH. So, say you have a phenol. You can alkylate this phenol with allylic bromide. All this is an SN2 reaction. Potassium carbonate, it's a base specializing in taking out protons that have pKa's of 10 and higher. It's a really good base at that. And then you end up doing an SN2. And then if you notice, this is set up for the 3,3 sigmatropic rearrangement. And so when you heat this up to do that rearrangement, you can get this. Now this molecule right here is actually unstable. I mean, it looks fine. But the thing is, that ketone has an enolizable hydrogen. And as a result, it tautomerizes This is one of the few examples where the enol form is actually more stable than the carbonyl form because of the benzene ring. And you get this. And if you take a look, here is our starting material. And in these two steps, we've added a carbon group ortho to it. Okay. So, that's the Claisen rearrangement. And that's all I have for today. So, we will have a last lecture on Friday, and there we will talk about some other sigmatropic rearrangements, one of which is actually very important to the University of Wisconsin. And that's essentially where led to the formation of the Wisconsin Alumni Research Foundation, which led to a huge amount of money for the University of Wisconsin. And one of the reasons why it's one of the most heavily funded research universities, public anyways, there is. So anyways, we'll talk about that on Friday.